All right. Welcome to another deep dive.
Yeah.
Today we're going to be looking at atoms and molecules.
Yeah.
Looks like we've got some really cool excerpts all about the fundamental building blocks of everything around us.
Hmm.
I think this is going to be really interesting. Now, maybe you're listening to this, you're studying for a chemistry test.
Sure.
Maybe you're just trying to brush up on some science.
Yeah, definitely.
Or maybe you're just curious.
Just curious. Yeah.
I'm already starting to think about some of these really cool questions from these excerpts, like
Yeah.
how did people even think about atoms, like way back when,
Right.
like when they had no way to see them?
Yeah.
How small are these things? And how did we figure out they even exist?
Great questions. Those are great questions.
Yeah, it's pretty mind-blowing when you think about it.
Absolutely. And it's really cool because it all starts with not in a lab,
Oh, interesting.
but with philosophers
Oh.
thinking about the nature of reality.
Okay, so they were like the original scientists, almost.
Yeah, they were asking this fundamental question.
Yeah.
And what's fascinating is, the excerpts mention ancient Indian and Greek philosophers.
Oh, yeah.
They had very similar ideas about matter, even though they were continents apart.
Wow, that's amazing. So like great minds think alike, right?
Yeah, exactly. It's really mind-boggling when you think about it.
So they were both like on the same track.
Yeah, across these huge distances and cultures, right?
Yeah.
Humans were thinking, like, what is the world made of?
Yeah, the most fundamental question there is, I guess.
Exactly. So in India, you had Maharishi Kanad, and he proposed this idea of Parmanu,
Parmanu.
which were these indivisible particles that make up, everything.
Everything, wow.
And in Greece, around the same time, you have Democritus talking about atoms.
Right, atoms, yeah.
And that literally means indivisible.
Oh, wow.
So both of them,
Yeah.
without any microscopes, without any fancy equipment,
Yeah.
came up with this idea that matter couldn't be divided infinitely. You had to get to like a smallest bit.
The smallest bit.
Yeah, a fundamental building block that couldn't be broken down further.
Wow.
It's a pretty revolutionary idea for their time.
It is. It's hard to even imagine, like, how they even came up with that.
Right.
With-
With what they had to work with.
Yeah. But that was all just like ideas, right?
Yeah, those were ideas, philosophical musings.
Right.
How do those ideas actually get tested?
Right.
How do they become actual, science?
Yeah, right. Because it's a long way from thinking about it to proving it.
Yeah, well, it took centuries. But in the 18th century, we start to see modern chemistry, right?
Okay.
With scientists like Antoine Lavoisier
Oh, yeah, Lavoisier.
doing these really rigorous experiments.
Rigorous. Yeah.
He's often considered the father of modern chemistry,
Yeah.
and for good reason, because he
Yeah.
really he
Yeah.
laid down the groundwork.
The excerpts actually mentioned that Lavoisier, like, established a couple of key laws
Yeah.
that were really important for understanding how elements combine.
Yeah.
One of them is the law of conservation of mass,
Right.
which basically means that matter isn't created or destroyed in a chemical reaction.
Yeah, it just changes forms.
It just changes forms. Yeah. There's a cool experiment that's described in one of these excerpts.
Okay.
You can kind of imagine, right?
Yeah.
You have these two solutions.
Mm-hmm.
They're carefully weighed, and you mix them together in a sealed container, and a chemical reaction happens.
Okay.
But guess what?
Mm.
The total weight stays the same.
Oh, interesting.
Isn't that cool?
Yeah. It's a simple experiment, but the implications are huge.
Right.
Because it tells us that the atoms,
Okay.
those fundamental building blocks,
Yeah.
they're still there. They've just rearranged themselves.
Rearranged.
Yeah, into new combinations.
Okay.
The total mass stays the same.
Right.
Because the atoms themselves haven't, vanished or
Yeah.
magically appeared.
Right, they're not going anywhere. Makes sense.
Mm-hmm.
Okay, so what about the law of constant proportions?
Right.
I remember something about fixed ratios.
Yeah, so Lavoisier and other scientists at the time,
Okay.
they observed that a compound, like let's say water,
Yeah, water.
always has the same elements combined in the same proportions by mass, no matter where you get it from.
So like water is always water.
Yeah, water's always water. It's always 2 parts hydrogen to 1 part oxygen,
Yeah.
whether it's from rain or a river or if you create it in a lab.
It's always the same.
Yeah,
That's wild.
it is pretty wild.
So those fixed ratios,
Yeah.
they kind of suggest that elements don't just like randomly mix.
Yeah, no, it's not random.
There's a specific recipe, right?
Yeah, there's a specific recipe for each compound.
For each one. Yeah.
And that observation was key because it kind of hinted at the existence of, these
Right.
fundamental units, atoms,
Yeah.
combining in these specific ways.
Okay.
Yeah.
So this brings us to John Dalton and his atomic theory.
Right.
Um, I kind of remember learning about this in school.
Sure.
But honestly, it seemed kind of abstract back then.
Yeah.
Now I'm looking at these excerpts, and I'm like, wow, his ideas were really groundbreaking.
Dalton's theory was a huge turning point.
It was.
Yeah, he took those existing laws and observations, the ones we just talked about,
Yeah.
and he built a scientific framework around them.
Wow. Okay.
It wasn't just philosophical ponderings anymore. It was like a way to understand and predict how matter behaves.
So it became a real science.
Yeah.
Okay, so what exactly did Dalton propose? I remember something about atoms being indivisible.
Yeah, right. Let's break it down.
Yeah, let's break it down.
Dalton had 6 main points to his theory, 6 postulates.
Postulates, okay.
First, he said, all matter is made up of these tiny particles called atoms.
Okay, atoms.
Atoms, that's the foundation of the whole thing.
It all starts there.
Yeah, like the ultimate Lego brick.
Okay, Lego bricks, yeah.
And then he said, atoms can't be created or destroyed in chemical reactions. That explains Lavoisier's law of conservation of mass, right?
Okay, they just rearrange.
They rearrange, yeah.
They don't appear or disappear.
Okay.
Yeah.
So is that why we still have the same amount of stuff in the universe today as like billions of years ago?
Pretty much, yeah.
It's just been rearranged.
Rearranged, yeah, into all these different forms.
Okay, that's amazing.
His third postulate was that atoms of a given element are identical in mass and properties.
Okay.
So all carbon atoms are the same,
Okay.
all oxygen atoms are the same, and so on.
Okay, so that's why each element has its own unique characteristics, because its atoms are different from the atoms of other elements.
Exactly.
Yeah.
Now, we know that's not entirely true
Yeah.
because of things like isotopes, which are
Yeah.
atoms of the same element with slightly different masses.
Okay.
But for Dalton's time, it was a huge leap forward.
Right.
His fourth point built on that.
Saying that atoms of different elements have different masses and properties.
Okay, so a carbon atom is fundamentally different
Yeah,
from an oxygen atom.
different.
So each element has its own unique atomic fingerprint, you could say.
Yeah, exactly.
That's so cool.
Yeah.
What about the last 2 postulates?
His fifth postulate was that atoms combine in whole number ratios to form compounds.
Okay.
No half atoms or fractions allowed.
Okay.
And that directly explained the law of constant proportions.
Right.
So those fixed ratios
Yeah.
observed in compounds
Yeah.
could be explained by atoms combining in simple whole number ratios.
Ratios. Okay.
Like 1 to 1, 2 to 3, and so on.
So it's like nature has a built-in system at the atomic level.
Yeah, it's pretty amazing.
And lastly,
His sixth and final postulate stated that the relative number and types of atoms are constant in a given compound. So water is always 2 hydrogen atoms and 1 oxygen atom,
okay.
no matter where it comes from or how it's made.
Yeah. Okay. So that fixed composition,
Yeah,
that's what gives the compound its unique properties.
exactly.
Dalton really laid the foundation
He did.
for modern chemistry.
Yeah.
Wow. So at this point, we have this idea of atoms as like these fundamental units
Yeah.
of matter.
Yeah.
But how did scientists figure out what different elements were made of?
That's a great question.
If they couldn't even see atoms,
Right.
it's like, how do you even begin with that?
Right. How do you even start?
Yeah,
It's mind-boggling to think about
it is.
that they were working with these incredibly tiny invisible entities.
It's crazy.
Yeah, they were working with these incredibly tiny invisible entities. So how did they figure out what distinguished one element from another?
Yeah, it's almost like they were working in the dark.
Yeah, in a way they were.
They had to like feel their way around.
Yeah, and it was this brilliant combination of deduction and experimentation
Okay.
and a little bit of, ingenuity.
Ingenuity, okay.
Dalton's theory proposed this idea of atomic mass.
Atomic mass.
Basically, the mass of an atom
Okay.
compared to a standard reference.
Standard of thought.
And that was like a stroke of genius.
Really?
Yeah, because it allowed scientists to work with relative masses,
Okay.
even though they couldn't actually measure the mass of a single atom.
Right, because they're so tiny.
Exactly.
Okay. So it's kind of like saying, all right, we don't know exactly how much a grain of sand weighs,
Right.
but we can say that a pebble weighs 10 times more.
Yeah, that's a great analogy. And by observing how elements combined in specific ratios,
Okay.
they could figure out their relative atomic masses. For example, if they found that 1 gram of hydrogen always combined with 8 grams of oxygen to form water,
Okay.
they could then infer that oxygen atoms were 8 times heavier than hydrogen atoms.
Okay, so they were just looking at the ratio.
Yeah, the proportions and the ratios.
Okay, I see that. That makes sense.
Yeah.
But what about the actual, units? What's the standard reference for atomic mass?
So today, we use carbon-12 as our reference point.
Carbon-12.
1 atomic mass unit, or a mole,
A move, okay?
is defined as 1/12 the mass of a carbon-12 atom.
Okay.
And from there, we can determine the relative atomic masses of all the other elements
Okay, I see.
based on how they combine with each other in reactions.
Gotcha.
Yeah.
So if, oxygen has an atomic mass of 16 mu,
Yeah.
it means that an oxygen atom is 16/12,
Right.
or about 1.33 times heavier
Yeah.
than a carbon-12 atom.
You got it. That's exactly right.
Okay, that makes sense.
And this system of relative atomic masses,
Right.
it allowed scientists to start organizing and classifying elements.
Oh, okay.
And that eventually led to the development of the periodic table.
Right, the periodic table, yeah.
Which we all know and love.
Yeah, everybody's favorite chart.
Exactly.
All right, but to really understand this, we need to kind of go, deeper
Yeah, we got to go deeper.
into the realm of subatomic particles.
Yeah, you mentioned earlier, the Russian nesting dolls, right?
Yeah, the Russian nesting doll.
The atoms aren't the end of the story.
Right.
They're made up of even smaller bits.
Smaller bits.
It's like peeling back the layers of an
Yeah,
onion.
like an onion, yeah.
What are these subatomic particles?
Yeah, what are they?
How do they all fit together?
And how do they make an atom?
So the 3 primary subatomic particles
Okay.
are protons, neutrons, and electrons.
Okay, protons, neutrons, and electrons.
And each one of these
Yeah.
plays a really crucial role in the atom's structure and behavior.
Okay, so they all have a specific job to do.
Yeah, they all have their jobs.
So protons,
Protons carry a positive electric charge.
positive.
Neutrons are neutral,
Okay, neutral, so they have no charge.
no charge.
Okay. And electrons carry a negative charge.
Negative. Okay, so we got positive, neutral, and negative.
You got it.
Okay, I think I can remember that.
All right, good.
But where are these particles in the atom?
Are they just kind of randomly scattered around?
Not at all.
Yeah.
There's a very definite structure here.
Okay, so there's a system?
Yeah, there's a system.
Okay.
Protons and neutrons, they cluster together in the center of the atom,
Okay, in the center.
and they form what we call the nucleus.
The nucleus.
And you can think of the nucleus as this tiny, heavy heart of the atom.
Okay, like the core.
Yeah, it's the core.
Yeah.
And it contains almost all of its mass.
Almost all the mass is in the nucleus.
Pretty much, yeah.
Okay, so that's the central hub, you could say?
Yeah, it's the central hub.
What about those negatively charged electrons?
Right.
Where do they fit in?
So the electrons are buzzing around the nucleus
Buzzing around, okay.
in regions of space called orbitals.
Orbitals. Okay.
And here's where the classic planets orbiting the sun model breaks down.
Oh, okay.
Electron orbitals aren't these neat circular paths.
Okay.
They're more like three-dimensional probability clouds.
Three-dimensional probability clouds. Wow, that's a mouthful.
I know, right?
Okay, so what does that even mean?
Imagine like a bee buzzing around a flower.
Okay, I can picture that.
You can't say exactly where the bee is.
Right, yeah.
At any moment.
But it's in that area.
Yeah, exactly. It's somewhere around that flower.
Okay, so the electrons are more like this blurry, buzzing cloud
Yeah, that's a great way to visualize it.
rather than little planets on fixed tracks.
Yeah, it's more like a fuzzy cloud.
Okay, so it's not as neat and tidy as we might picture it.
No, not at all.
Okay, that's interesting.
Each orbital has a different shape and energy level.
Okay.
And the arrangement of those electrons in the orbitals
Okay.
really determines how an atom interacts with other atoms.
So it's like each atom has its own unique electron dance party going on.
I like that. Yeah, it's like a little dance party.
Yeah.
And that dance party determines
Okay.
how they bond with each other to form molecules.
To form molecules. Okay.
Yeah.
So how do these subatomic particles determine the properties of an element? Like, what makes gold so different from, let's say, carbon?
Well, it all boils down to the number of protons in the nucleus,
Protons. Good.
which we call the atomic number.
Atomic number.
And that's like the ID card of an element.
The ID card. Okay.
All carbon atoms, for example,
Yeah.
they have 6 protons.
That's 6 protons.
All gold atoms have 79.
There's 79. Okay.
So that's what gives them their unique atomic fingerprint.
Their fingerprint. Okay, so the atomic number tells us exactly what element we're dealing with.
Exactly.
Okay, what about neutrons? We haven't talked about them too much.
Right.
What's their role?
They're important because they contribute to the atom's mass.
Okay, they add to the weight.
Yeah, they add to the weight,
Okay.
but they don't affect its chemical properties.
Okay, interesting.
Atoms of the same element can have different numbers of neutrons.
Yep.
And these variations, we call them isotopes.
Isotopes.
So, for instance, carbon-12 has 6 neutrons.
Okay.
Carbon-14, which is radioactive,
Oh, yeah?
and we use it to date fossils, that has 8 neutrons.
8. Okay.
So they're both carbon,
Yeah.
but with slightly different masses.
So they're like siblings, kind of
Yeah.
with slightly different personalities.
Yeah, that's a great way to think about it.
But they're still part of the same family.
Exactly.
Okay, that makes sense.
Now, here's a question for you.
Okay, hit me.
We've got these negatively charged electrons buzzing around a positively charged nucleus.
Yeah.
Why don't they just crash into each other?
That's a good question. I mean, opposites attract, right?
Yeah.
It seems like they should be drawn together.
Right. So what keeps them apart?
What's stopping them from just collapsing in on each other?
It's the electromagnetic force.
The electromagnetic force. Okay.
The electrons are attracted to the protons,
Okay.
but they also have kinetic energy,
Kinetic energy, all right.
which keeps them in motion
Okay.
around the nucleus.
Okay.
It's a delicate balance
Okay.
of attraction and motion.
It's like this cosmic dance
Yeah, like a dance.
where they're constantly, like, drawn to each other,
Yeah.
but never quite collide.
They never quite touch.
Wow, that's amazing.
And the arrangement of those electrons in their orbitals
Okay.
dictates how the atom interacts and bonds with other atoms.
Bonds with other atoms. Okay.
So atoms are always looking for stability.
Stability. Okay.
And they can achieve that by gaining, losing, or sharing electrons with other atoms.
With other atoms. Okay, so they could do a few things.
Yeah, there are a few options
Right.
to get to that stable state.
Wait. If atoms can gain or lose electrons, doesn't that, like, change what element they are?
Ah, that's a really important distinction
Okay.
between chemical reactions
Okay.
and nuclear reactions.
Nuclear reaction. Okay, so those are different.
They're very different.
Right.
In a chemical reaction, it's only the electrons that are involved.
Okay, only the electrons.
Yeah, the nucleus. That stays untouched.
The nucleus stays the same.
Yeah, it's like the core of the atom.
Okay.
It doesn't change.
But if the electrons change.
Yeah, when an atom gains or loses electrons,
Okay.
its charge changes,
Okay.
and it becomes what we call an ion.
An ion.
An ion, yeah.
Okay, so an ion is just an atom that has an electric charge.
Yeah, because it's either gained or lost some electrons.
Okay, so it's either got too many
Right,
or not enough.
exactly.
Okay.
So if an atom gains electrons,
Yeah.
it becomes negatively charged.
Okay, negative.
And it's called an anion.
An anion.
Think of an anion as having like an extra electron.
An extra.
If it loses electrons, it becomes positively charged.
Okay, positive.
And it's called a cation.
A cation.
And that means it's like missing an electron.
It's missing what? Okay, so it's got a positive charge.
Exactly.
Gotcha. So those positive and negative charges,
Yeah.
those are what allow ions to form bonds.
Yeah.
Right?
That's right.
Like in salt, which is
Yeah.
made of sodium and chlorine ions.
Exactly.
Sodium chloride.
So the positively charged sodium ions
Okay.
and the negatively charged chloride ions,
Yeah.
they're attracted to each other
Okay.
and they form a strong bond.
They bond together.
Yeah, and that creates a crystal lattice structure.
A crystal lattice structure.
And that's what gives salt its characteristic properties.
Okay, so it's like this giant game of magnetic attraction
Yeah, it's like magnets.
with positive and negative ions sticking together.
Exactly.
Okay, we call those ionic bonds.
Ionic bonds, yeah.
Right, and those are strong, right?
They're very strong. That's why ionic compounds tend to have high melting and boiling points.
Okay, so it takes a lot of energy to break those bonds apart.
Exactly.
Okay, ionic bonds. I think I'm getting it.
Good. Good.
So we've got atoms
Yeah.
made up of protons, neutrons, and electrons.
Right.
And atoms can bond with each other to form molecules
Yeah.
by gaining, losing, or sharing electrons.
That's right.
It's like this complex dance
It is. It's a dance.
of attraction and repulsion.
Exactly.
Okay, so are there other types of bonds that atoms can form?
You bet. Another important type is the covalent bond.
Covalent bond.
Okay, and that's where atoms share electrons to achieve stability.
They share. Okay,
Mhm.
so instead of one atom hogging all the electrons,
Yeah.
they decide to be nice and share them.
They share like good roommates.
That good roommates, yeah.
And the shared electrons, that's what holds the atoms together in the molecule.
Okay, so that's the glue, kind of.
Yeah, it's the glue.
The covalent bond.
Exactly.
Okay, and these are common in molecules of nonmetals, right?
Yeah, you see them a lot in nonmetals.
Like the oxygen we breathe.
Right, oxygen is O2,
O2, yeah.
water, H2O,
H2O. Okay.
and carbon dioxide, CO2.
CO2, gotcha.
So those are all examples of covalent bonds.
Okay.
Yeah.
And covalent bonds are really important in organic chemistry, right?
Yeah, organic chemistry is all about covalent bonds.
Which is the chemistry of life.
Exactly, the chemistry of life.
Okay.
So think about DNA, proteins, carbohydrates.
That's good stuff.
Yeah, all the essential building blocks of life.
Okay.
They all rely on covalent bonds.
It's incredible to think that these tiny interactions, these bonds, are what makes up everything.
It really is amazing.
It's like a secret code that governs the whole universe.
It's a blueprint.
A blueprint, yeah.
For how matter behaves.
Okay, so I have a question.
Okay, sure.
We've been talking about atoms gaining or losing electrons to become ions.
Right.
And about atoms sharing electrons to form covalent bonds.
Right.
But how do they decide which path to take?
That's a fantastic question.
Yeah, like how do they know what to do?
What determines whether they're going to form an ionic bond or a covalent bond?
Yeah, like what's the rule?
The answer lies in this concept called electronegativity.
Electronegativity.
And it's a measure of an atom's attraction for electrons.
Okay, so how much they want to grab those electrons?
Yeah, exactly. Think of it like this.
Okay.
Some atoms are really electron hungry.
They want those electrons.
Yeah, they're greedy.
Okay.
While others are more willing to share.
And generous, okay.
Yeah, so if you have two atoms. Okay.
With very different electronegativities.
Okay. One's greedy, one's not.
Yeah, one will tend to pull the electrons away from the other.
They're going to hog them.
Yeah, they're going to hog them. And that forms an ionic bond.
Okay, so that's ionic.
Yeah.
But if they're more similar...
Yeah, if the electronegativities are closer,
okay,
they're more likely to share those electrons.
they're going to be nice.
They're going to be nice.
And that's covalent.
And that's covalent, exactly.
So it's all about how greedy they are for electrons.
Yeah, that's a great way to think about it.
It's like some atoms are playing tug of war with electrons.
Yeah, tug
And others are happily sharing their toys.
Exactly.
Okay, I like that analogy.
And that simple concept of electronegativity
Yeah.
really helps explain why we see such a variety of bonds and molecules in the world around us.
Okay.
It's all about how those atoms interact
Yeah.
based on their inherent desire for stability.
Their desire for stability, okay, they want to be balanced.
They want to be balanced.
All right, that makes sense.
Yeah, this is so fascinating. It's amazing how much complexity
Oh, I know.
arises from these simple building blocks and their interactions.
Right.
I'm starting to see the world in a whole new way.
That's what it's all about.
It's like looking through a microscope at everything.
Yeah, you're seeing the hidden world.
All right, so let's keep going. Let's explore some more of these fascinating concepts related to atoms and molecules.
Okay, let's do it.
Okay, so we're back
Yeah.
and ready to learn more. I mean, we've been talking about all these tiny things, atoms and electrons and even smaller. It's wild to think that everything we see and feel
It is.
made of these little guys and how they interact.
Absolutely. And as we go deeper, we find even more fascinating concepts that can help us understand how matter behaves.
Okay.
One of those concepts is molecular mass.
Molecular mass.
We've talked about the masses of individual atoms, right?
Right, like how heavy one atom is.
Yeah, but what about the mass of an entire molecule?
Yeah, how do you weigh something like that?
Well, it's actually pretty straightforward. You just add up the masses of all the atoms in the molecule.
Oh, so it's like if I have a basket of fruit
Yeah, exactly.
and I know how much each apple, orange, and banana weighs,
Right.
then I can just add those up to find the total weight.
Exactly. It's simple addition.
Okay, that makes sense.
So let's take a simple molecule like water.
H2O.
Right, H2O. So the molecular mass
Yeah.
would be the sum of the atomic masses of 2 hydrogen atoms
Right.
and 1 oxygen atom.
Okay.
Now, we know hydrogen has an atomic mass of about 1 mu,
1 ml.
and oxygen's about 16.
Okay.
So the molecular mass of water would be...
Let's see, 2 times 1 plus 16.
Yeah.
So 18 a mu.
Exactly,
Yeah.
18 mu.
Okay, simple enough.
Yeah.
But what about ionic compounds like salt?
Good question.
We talked about how they don't exist as discrete molecules.
Right.
They're just those, like, big networks of ions.
Exactly. Giant networks held together by electrostatic forces.
So how do you calculate the mass of something like that?
That's a great point. For ionic compounds, we use the term formula unit mass
Formula unit mass.
instead of molecular mass.
Okay, why is that?
Well, it represents the mass of the simplest ratio of ions in the compound.
The simplest ratio.
So for sodium chloride,
Yes.
NaCl, the formula unit mass would be the sum of the atomic mass of 1 sodium atom
Okay.
and 1 chlorine atom.
Okay, so we're still just adding up atomic masses.
Right.
But we're using a different term for ionic compounds.
Exactly, because they don't form distinct molecules the same way covalent compounds do.
Hmm. Okay, that makes sense.
Now, another concept that can help us understand the diversity of molecules is atomicity.
Atomicity. Okay, what's that?
It refers to the number of atoms
Okay.
that combine to form a molecule.
So it's like how many atoms are hanging out together.
Yeah, basically, just a head count.
Okay, so if it's just a number, why is it important?
Well, even though it seems simple, it actually has huge implications for a substance's properties.
Okay, so the number of atoms really matters.
Yeah, take oxygen, for example.
O2.
Right, it exists as a diatomic molecule.
But meaning two atoms.
Exactly. Two oxygen atoms bonded together.
Okay.
And that structure gives oxygen its unique characteristics.
Okay.
Makes it essential for life as we know it.
Right. Gotta breathe.
Exactly. Now, what about elements that exist as single atoms?
Like just one atom floating around?
Yep, all by themselves.
Is there a name for those?
We call them monatomic elements.
Look, atomic, okay.
Good examples are the noble gases.
Like helium?
Helium, neon, argon, those guys.
Oh yeah, they just like to be alone.
Exactly. They're content as single atoms, which makes them very unreactive.
Kind of like the introverts of the periodic table.
Huh. I love that. Now, on the other end of the spectrum,
Okay.
we have polyatomic molecules.
Polyatomic.
They contain more than two atoms.
More than two, okay.
So sulfur, for example, often exists as S8.
Yeah.
It's a ring of 8 sulfur atoms bonded together.
Wow, a ring, that's cool.
And phosphorus forms a tetrahedral molecule, P4, with 4 phosphorus atoms.
Okay, so some molecules get pretty crowded.
They do. It's amazing how these atoms arrange themselves in such intricate structures.
It is, but how did scientists figure out the atomicity of different molecules?
Right, how they know oxygen was diatomic or that sulfur was S8.
Yeah, it's not like they could just count the atoms.
Well, it was a combination of observation, experimentation, and deduction.
So real detective work.
Exactly. They studied how elements reacted with each other,
Okay.
carefully measuring the masses of the reactants and products.
The inputs and outputs.
Yeah, and by analyzing those ratios, they could infer the formulas of the compounds being formed.
Okay.
And that helped them figure out the atomicity of the molecules involved.
So it was like a puzzle. They had to piece together clues from reactions to figure out how many atoms were in each molecule.
Exactly. And over time, they developed different techniques to determine molecular structures more directly.
Okay, so they got better tools.
Yeah, things like spectroscopy and X-ray crystallography.
Oh, well, those sound fancy.
They are. And they let us actually visualize the arrangement of atoms within a molecule.
So we've gone from blind guessing to basically having a camera for the molecular world.
That's a great way to put it. And with that knowledge, we can do amazing things.
Yeah, like what?
We can design new materials, develop new medicines,
That's-
and even manipulate matter at the atomic level.
Wow, that's incredible.
It is. It's all thanks to understanding these tiny building blocks and how they interact.
It's crazy to think that everything we see and experience comes from these tiny interactions.
I know, it's mind-boggling. And we've just scratched the surface. There's so much more to learn.
I feel like we could keep talking about this forever.
Yeah, probably. But for now, we should probably wrap things up.
Okay, so I think it's safe to say we've had a pretty incredible journey today.
We have.
We started with these ancient philosophical ideas about atoms.
Yeah.
And now we're talking about, like, visualizing molecules and manipulating matter.
It's a testament to human curiosity and the power of scientific inquiry.
Totally.
Yeah.
And what's really exciting is that there's still so much more to discover.
Oh, absolutely.
Dalton's theory was revolutionary,
It was.
but we've come a long way since then.
Yeah, we've learned that atoms are made of even smaller particles.
Right, even smaller. It's like an endless journey into the heart of matter.
It really is. Who knows what incredible discoveries await us in the future?
That's the best part, right? There's always more to learn.
Exactly. Well, it's been awesome sharing this deep dive with you.
Yeah, this has been a blast. We've explored the tiny building blocks that make up everything we see and feel.
It's a reminder that the world is full of wonder, even at the smallest scales.
Absolutely. Thank you for joining us on this adventure. We hope you've learned something new.
And maybe sparked your own curiosity about the world around you.
And remember, the quest for knowledge is never ending.
So keep asking questions, keep exploring, and never lose your sense of wonder.
Couldn't have said it better myself. Thanks again for joining us.